Hi, thanks for joining me. Today I'm going to be showing you a really cool theorem all to do with polynomials and their roots. This is known as Descartes' Rule of Signs. Now, what is it? Well, I've just drawn up an example polynomial. What I'm going to do is kind of use this as an example to explain what the whole theorem is about. Anyway, we have this polynomial p of x that's x to the 7 minus 3x to the 5 plus 7x to the 4 plus 12x cubed minus 11. Now, what we're concerned with is the number of positive real roots to p. So the number of positive real numbers, which when you plug into this guy p, you're going to get 0. Now what I can do straight away is this looks like a complex polynomial, but I can straight away tell you that that number of roots, so the number of positive roots, which I'm going to denote z of p, is going to be less than or equal to the number of sign changes of p. So in other words, when you're reading this from left to right, the number of times it changes sign. So what do I mean by this? Well, here we've got like an imaginary positive 1 here. So that's positive. But here we go negative, so that's one sign change going from here to here. But here we're going negative to positive, so that's another sign change, so that's 2 sign changes. Here to here is positive to positive, so that's not a sign change, that's fine. And here to here is plus to minus, so that's another sign change. So that's 3 sign changes in total. So I claim that the number of positive real roots to this polynomial p of x is less than or equal to 3. And what's amazing is that this is true, but also it holds in general that if you want to know or you want to find an upper bound to the number of positive real roots to a polynomial, you can do this. So by looking at the number of times the polynomial changes sign, which I think is bizarre, but what's amazing is the proof for it is really, really straightforward. Let's prove this. Okay, so before we get stuck into the main part of the proof, I need to quickly state and prove a lemma. If we take a generic polynomial p of x, which equals a0 times x to the b0 plus a1 times x to the b1, and so on all the way up to an times x to the bn, and we've written it in this sort of non-standard form because we want each of the ai's to be non-zero. So we're basically taking the normal notation of a polynomial, but then we're removing any of the terms which are non-zero, and hence why we've got b0, b1, and bn in the exponents as opposed to 0, 1, 2, 3, all the way up to n. Anyway, if a0 times an, so the coefficient of the smallest power of x times the coefficient of the largest power of x, when you multiply them together, if you get a positive number, then z of p is even, otherwise z of p is odd. So if you multiply these two and get a negative number, then z of p is odd. And z of p here, remember, is just the number of positive real zeros of this function p. But one thing I forgot to mention is that includes multiplicities. So for example, if we have this function p of x here, which is a quadratic and it just touches the real axis, so then it comes back up, then z of p of that guy would be 2 because it touches the positive real axis kind of at it's a double root there. Anyway, to prove this, hopefully it's kind of straightforward to see this, but I'm just going to prove it in the case where a0 and an are positive. So the proof when a0 and an are both negative is kind of similar, and when one's positive and one's negative, i.e. this case here, it's another very similar thing. But the main idea is we're just going to sketch a graph. So we're going to assume that a0 is positive and an are positive, so that's sort of one case of this guy here. And also one thing we can do is we can assume without loss of generality that b0 is 0. Why can we do that? Well, if b0 is bigger than 0, then we can kind of just factor out x to the b0 from this guy here, and we'll still be left with x to the b0 times some polynomial, but that polynomial is still going to have the same positive real roots as p of x, because the only thing we've taken out is x to the b0, and the only real roots of that are x equals 0, so that won't count towards z of p. So without loss of generality, we can assume b sub 0 is 0. Okay, so that means when you plug in x equals 0 into this guy, so if we assume this is 0, so in other words this is a constant term, when we plug in x equals 0 into this guy here, we're just going to get a0, which we're assuming is a positive number. So it's going to come through like that. And because an is positive, this guy here, the graph is going to go off to infinity. So as x tends to infinity, this whole polynomial is going to tend off to infinity. So it's going to go off to infinity like that. And it passes through this point here. Now in between, we want to know the number of times it crosses this real axis. But notice if it crosses, then to end up there, it's got to cross back at some point. We don't know when. It could, do a bit of faffing about or something first, but it's got to cross back. And once it's crossed back, it could dip back down again or whatever. And every time we do that, we're sort of alternating, going from top to bottom and then bottom back to top, and that's going to constitute 2 towards ZP. So each time we sort of pass through the axis, we're going to get pass through the axis and come back out again. We're going to get an extra 2, and hence why Z of P is even. And now you might worry about what happens if there's a multiple root. If there's a multiple root, say, let's just add it on here. If it does something like that, well then remember that we said that if that happens, we're going to add 2 to the root. So again, that's just going to keep adding 2, and that's essentially as if it were to go through and then up again. Anyway, we're just essentially adding 2 every time we pass and come back through this real axis, and hence Z of P is even, because we're just adding 2 some number of times to 0, and hence we're going to be left with an even number, and then of course this will go off to infinity in the end. Okay, so Z of P is even in the case A0 and AN are positive, and it's very similar in the case when they're both negative, and in the case where one's positive and one's negative, you'll see that Z of P is odd. Anyway, that's a bit of a sketch proof. Now let's get on to the main proof of Descartes' Rule of Signs. Okay, so now we can get into the main part of the proof. Firstly, let's introduce some notation. I've written V of P here to be the number of sign variations in P. So that's when you read the polynomial P of X from left to right, the number of times the coefficient sign change. So in the example I gave, V of P was 3. Okay, now we claim that Z of P is less than or equal to V of P. But what's actually really interesting about this proof is that we actually have to prove this result simultaneously to prove the first result. So we're actually going to be proving these two things here. What's the second guy? Is that Z of P is congruent to V of P mod 2. Okay, so in other words, they have the same parity. Okay, remember the Descartes rule of signs is just that Z of P is less than or equal to V of P, but we actually have to prove both of these guys together. Anyway, how are we going to prove it? We're going to prove it by induction, and induction on the degree of P. So P is a polynomial, so it has some degree, and we're going to prove it by induction on the degree of P. So let's look at the base case when P of X, when the degree is just 1, degree of P is just 1. So that means that P is just a linear function. So we can write P of X equals alpha X plus beta for alpha and beta real numbers, and where alpha is non-zero. Well, firstly, if let's look at the case if alpha beta is positive, so alpha times beta, if you get a positive number. Obviously, if this is 0, well, that implies that beta is 0 because alpha is non-zero. So if this alpha times beta was 0, then that would mean that beta is 0. So we just got P of X equals alpha of X. But clearly there are no sign variations, but also there are no positive roots because the only root of that guy will be X equals 0. So we're going to get that Z of P equals V of P equals 0. So that does both of these guys in one. So we can assume without loss of generality that alpha and beta are both non-negative. So alpha, beta, not 0. Okay, so for case 1, if alpha and beta are positive, well, then what are the number of roots? What's Z of P? Well, if we just sketch a graph, if alpha and beta are both positive, then if we set this equal to 0, we get that X is just equal to minus beta over alpha. But because they're both when you multiply them together, you get something positive. That means that alpha and beta have the same sign. So that means that minus beta over alpha will be some negative number. So that it's going to look something like this. Okay, so it only has one root, but it's negative. So Z of P is 0 because it's got no positive real roots. Cool. What about V of P, the number of sign variations? Well, that's also clearly 0 as well because alpha and beta have the same sign. So going from here to here, they have the same sign, so V of P is just 0. Perfect. So that proves this guy here, because 0 is certainly less than or equal to 0, and it proves this guy here, because 0 is equal to 0 mod 2. Now let's look at the second case where alpha and beta have different signs, like so. Then very clearly V of P is going to be equal to 1. Okay, but because alpha beta is negative, if you just have a look at this guy here, the thing we just had, if we look for the roots of P of X, X is going to equal minus beta over alpha again. So P of X equals 0 implies that X equals minus beta over alpha. But because alpha beta is less than 0, that means that alpha and beta have different signs. So that means that minus beta over alpha is going to be positive. So the real root of this guy here is going to be some positive real number. So that tells us that Z of P is equal to 1 as well. So again, we get the equality in the first case. So z of p is less than or equal to v of p because 1 is less than or equal to 1, and they're also the same mod 2. Okay, so that proves the base case. Let me clean up the whiteboard and we'll carry on. Okay, so now we're going to assume that our claim holds true for all polynomials of degree k, where k is just some natural number. Now remember, our claim is just z of p is at most v of p, and that z of p is congruent to v of p mod 2. Now our inductive step, we're going to introduce a polynomial of degree k plus 1, so I've just labelled this generic polynomial here, a0 times x to the b0 plus a1 times x to the b1, and so on all the way up to, I've labelled this a tilde times x to the k plus 1, and the reason it's a tilde and not a sub k plus 1 is because some of these ai's could be 0, so technically this would be a smaller a, but it doesn't actually matter what we notate it with, it's just some real number, times x to the k plus 1. So here we've got a polynomial of degree k plus 1. Now what we want to do, first thing we can do is actually, like before, assume without loss of generality that b0 is 0, because again, if it's not 0, we can just factor out x to the b0, and then what we're left with will be x to the b0 times some polynomial, and that polynomial will have the same z value and v value as this guy here, so we can just focus on the sort of reduced polynomial with a constant term here. So we can assume b0 is 0, so we can get rid of this x to the b0 like so. And what we're going to do is, to use our assumption, we're going to be considering the derivative of p. But before we do that, we're going to split this guy into two different cases. So remember, each of these ai's are non-zero. That's why we've got these b1s and stuff. So we're just essentially taking our polynomial and getting rid of the 0 terms. So case 1 is going to be, if a0 times a1 is positive. And then after that, I'll look at the case where a0 times a1 is negative. But what this tells us is that a0 and a1 have the same sign. Now, when I look at the derivative of this guy here, so p prime, this a0 will vanish, and everything here will have the same sign as before, but obviously this a1 will now be an a1 times b1, but obviously each of these bi's are positive numbers, so that's not going to change the sign of them. So in other words, the number of variations in p prime is actually going to be the same as the number of variations in p, the sign variations in p, because the first sign variation in p is going from here to here. We're assuming that a0 and a1 have the same sign, so there's not going to be a sign variation there. So the first sign variation is going to come after that. So when we look at the derivative of p, so let me just write it out here explicitly, a1 times b1 times x to the b1 minus 1 plus dot 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 plus a tilde k plus 1 x to the k, like so. The first sign variation from this guy is going to come after a1, so it's sort of here as well. So the number of sign variations in here, or any sign variation here, is going to correspond to one here, and vice versa. Hence, v of p prime equals v of p. Now, what about z of p prime? Well, if we go back to our lemma from before, z of p prime, our lemma from before said that if we look at this guy here, if we multiply a0 and a tilde together, if we get a positive number, then z of p is even, otherwise z of p is odd. But notice that a0 times a tilde is going to be the same as, is going to have the same sign as a1 times a tilde times k plus 1. The k plus 1 doesn't really change things because it's positive. But a0 times a tilde is going to have the same sign as a1 times a tilde because of this guy here, because a0 times a1 have, a0 and a1 have the same sign, and hence a0 times a tilde will have the same sign as a1 times a tilde. So in other words, z of p for this guy here is either going to be odd or even, but it's going to be the same as this guy here, because a0 times a tilde, so essentially the coefficient of the first term times the coefficient of the last term is invariant, and hence they're either both odd or they're both even. Either way, we have that z of p is congruent to z of p prime mod 2, like so. So that's what we get from essentially this guy here. Now what we can do is use our assumption steps as, the fact that we know that it holds true for polynomials of degree k as well, and remember p prime is a polynomial of degree k, so we know that z of p prime is less than or equal to v of p prime, and we also know that z of p prime is congruent to v of p prime mod 2. We can combine all these together to prove what we want for z of, we want to prove that z of p is less than or equal to v of p. Well, z of p is, well, firstly let's prove this guy here, z of p is congruent to v of p. Well, z of p is congruent to z of p prime, and that's congruent to v of p prime because of this guy here. So z of p is congruent to z of p prime, z of p prime is congruent to v of p prime, and v of p prime is just, v of p prime is just v of p. So of course they're congruent to one another, and we get this guy here. So that proves this second bit here. Okay, so to prove that z of p is less than or equal to v of p, we actually have to use something called Rolle's theorem, which is a very fancy way of proving something kind of intuitive. But if you just think of any sort of graph, like so, and we're going to consider any two roots, so any, in this case positive roots, but any two roots of a function, and it's a continuous function, which polynomials certainly are, then if it passes through these 2 points, then certainly somewhere in between, the derivative has got to be 0, because it's either going to do something like this to do that, or maybe something like this. Okay, but you can clearly see it's got at least one point where the derivative is 0. It could have many points where the derivative is 0. It could do something like this and then pass through. Okay, but basically between any two zeros of the function, we're going to have at least one point where the derivative is 0. Okay, and that's the fancy way of saying that is Rolle's theorem. So if you've not heard of Rolle's theorem, perhaps you want to look that up and see the proof of it, but we're just going to sort of take it for granted because it is kind of intuitive. But essentially what that tells us is that z of p prime is greater than or equal to z of p minus 1. Okay, because between any two roots, we certainly have at least one point where the derivative is 0. Now what we can do is we want to prove that z of p is less than or equal to v of p. So z of p is less than or equal to z of p prime plus 1, which we know is equal to v of p prime, is less than or equal to v of p prime plus 1, because remember z of p prime is less than or equal to v of p prime, but we've just proved that z of p has the same degree, same residue mod 2, so it's either odd, they're either both odd or both even, and v of p prime we know is just the same as v of p plus 1. So z of p is less than or equal to v of p plus 1, but because z of p and v of p have the same parity, they're either both odd or they're both even, z of p can't equal v of p plus 1, otherwise they'll have different sort of parities, and hence z of p must be at most v of p. So you have to use a little parity argument there to get this inequality, but z of p must be at most v of p, because they can't be equal, and obviously z of p and v of p are integers, so z of p must be at most v of p. Anyway, that proves it in the case that a0 times a1 is positive. Now let's look at the case where that product is negative. Okay, so we now look at the case where a0 times a1 is negative. Like before, we can use Rolle's theorem to get this guy here, that z of p prime is bigger than or equal to z of p minus 1. But now when we consider v of p, there is a sign variation going from a0 to a1, because a0 and a1 have different signs. Essentially by looking at this case, a0 times a1 is negative. So these guys have different signs, so there is a sign variation. So when we look at the derivative of p, when we get rid of this a0 term here, we're essentially losing a sign variation. So we get that v of p prime is equal to v of p minus 1. Now actually from our lemma before, that we proved right at the start of this solution, was that if we take our first term and our last term, multiply them together, and we get a positive number, we're going to get something even. Z of p is even, and if we multiply them together and get a negative number, then z of p is odd. Well, notice here that the derivatives, so a0 and a1 have different signs. So if I just explicitly write down what p prime is, it's a1 b1 x to the b1 minus 1 plus dot 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 plus a tilde times k plus 1 x to the k. But notice that a1 and a0 have different signs, and hence when I do a1 times a tilde, that's going to have a different sign to a0 times a tilde. And these b1s and k plus 1 don't really affect anything because they're positive. So a1 times a tilde, or a1 times b1 times a tilde k plus 1, has a different sign to a0 times a tilde from the fact that a0 and a1 have different signs. And what that tells us is that the parities of z of p prime and z of p are going to be different. So one's going to be odd and one's going to be even. We don't know which, but we do know then that tells us that z of p prime is congruent to z of p plus 1 mod 2. Okay? Now what we can do is use these facts together to prove this guy here for p. So let's prove the second one first. Z of p is congruent to v of p. So z of p well, we know is congruent to z of p prime minus 1. Okay, but z of p prime by assumption we know is the same as v of p prime. But v of p prime, of course this minus 1 is the same as plus 1 because we're working mod 2. Doesn't really matter. But yeah, minus 1 is the same as plus 1 mod 2. So v of p prime is the same, z of p prime plus 1 is congruent to v of p prime plus 1. But if we just look at this guy here, that of course is just the same thing as v of p. So of course it's going to be congruent to v of p mod 2. So we get that z of p is congruent to v of p mod 2. Now let's prove that z of p is less than or equal to v of p. So z of p, we're going to start off with this guy here, is less than or equal to z of p prime plus 1. But z of p prime plus 1, well, we're assuming that z of p prime is less than or equal to v of p prime from our assumption. Okay, and v of p prime, using this guy here, is just v of p minus 1. So v of p minus 1 plus 1 is just the same as v of p. So we get that z of p is at most v of p, and that proves Descartes' rule of signs. A really, really nice proof. There aren't many proofs that I know, at least off the top of my head, where you've got to kind of prove two things simultaneously to get the result you want. But I think it's a really, really neat idea, and something that's, this theorem as a whole, it's something really, I don't know how you'd even think of, looking at the number of times the sign changes in the polynomial to work out not just not the number of real roots, but the number of positive real roots. And you can actually do something really similar with negative real roots, just by plugging in minus x into your polynomial p of x, and you can get a very similar theorem. But this is essentially the main idea, and the proof is really, really, it's a lot simpler than I thought it would be for a theorem which seems kind of complex. Anyway, I'm going to stop waffling. I hope you have enjoyed this video. Thanks for watching. I'll catch you in the next one. Have a great day.